As we get into rotational motion, we need to start with some fundamentals. For example, units. What units do we use for rotational motion? Well, one unit you're very familiar with, the radian. That's our unit for angle. And if we use radians for angle, then omega would be radians per second, and alpha would be radians per second squared. But that's not the only unit we can use for angle. We can use degrees, and then degrees per time, or degrees per second, and degrees per second squared for our acceleration alpha. But those aren't the only units we can use for rotation. What's another common unit we use? Maybe you've purchased a motor recently. How is it rated? In revolutions. Revolutions per minute are typical units for the rotational speed of a motor. Typically, we would use seconds in our class, but revolutions per time for omega, and revolutions per time squared, I'll write seconds squared for alpha. And in a lot of cases, it doesn't matter which set of units we use as long as we're consistent, as long as we stay within one of these rows. We can use degrees for theta as long as we use degrees per second and degrees per second squared for omega and alpha. This is true when we use our kinematics equations, for example, because the units cancel out if we do everything properly. But there are a couple of equations where we have to be in radians. For example, we often use this relationship. Here's a situation where we have a radius r and an arc length s and an angle theta. And we know that there's a relationship between the arc length and the angle and the radius. S, the arc length, is equal to the radius times the angle theta, if theta is in radians. So if theta is in radians, we can use this relationship. The arc length is equal to the radius times the angle. The arc length is the distance, right? The linear distance that our object traveled. This relates the linear distance with the angular distance. And if we take the derivative of this, we get ds dt, which is the tangential velocity, the linear velocity, is equal to r d theta dt, which is omega. And if we take the derivative of this, we get the rate of change of our tangential velocity, which is our acceleration, right? Our tangential acceleration, or our linear acceleration, a, is going to be r times alpha. So we need these relationships quite often to go back and forth between our rotational variables and our tangential variables. And if we're using these relationships, we must be in radians. Radians for theta, radians per second for omega, and radians per second squared for alpha. So if we're looking down from above at a merry-go-round, and person A is standing halfway between the center and the rim, and person B is standing all the way out there at the edge of the merry-go-round, and this is rotating, person A is taking this path, person B is taking this path, and I want to know who's going faster. Well, it depends how you think about things, right? One person might say, I'm thinking about things in terms of linear or tangential speed, translational speed. And if you're thinking in those terms, who's going faster? Person B. Person B covers a larger distance in the same amount of time. The translational speed, the linear speed, the tangential speed, those are all ways of saying the same thing, is greater for person B. They're covering the bigger distance in the same amount of time. But another person might come along and say, wait a minute, both of these people complete a revolution in the same amount of time. So they both have the same rotational speed. Omega A is equal to omega B. They are part of a rigid object, and every point on a rigid object has the same omega. Every point on a rigid object has the same rotational speed, the same angular speed, because every point completes a revolution in the same amount of time. But as you go out farther and farther away from the rotational axis, your linear speed has to increase because you're covering a bigger distance in the same amount of time. And what's the relationship? Well, we just talked about it right here. The relationship between the two speeds, v, is equal to r omega. We also have that same relationship for the distance covered and for the acceleration. Maybe you noticed that these are vector quantities. We need to define a direction for our vector quantities, a direction that we can all agree on. Here I have a wheel, and I'm going to start it rotating. How would you describe this rotation? I bet some of you are thinking clockwise. But I'm looking at the wheel too. And I'm telling you it's not going clockwise. It's going counterclockwise. I'm looking right at it. It's going this way. That's counterclockwise from where I'm standing. We need something we can all agree on. In physics, when we want to define a plane, we don't pick anything in the plane to define the plane. We pick a vector normal to the plane, a vector perpendicular to the plane, and we say that vector defines the plane. We do the same thing for rotation. If we have an object, like this wheel, rotating, we'll pick a vector that's perpendicular to the wheel to define the direction of rotation. We just have to decide which way does it point. It's going to point along the axis of rotation. Does it point toward the camera or does it point toward me? Well, we use a right-hand rule. We have lots of right-hand rules in physics, but we don't have any left-hand rules. Lots of right-hand rules. This is one of them. What we do is we take our fingers on our right hand and we let them roll around in the direction the object is rotating. And our thumb points along the axis of rotation. So if this object is rotating this way, my fingers have to go in the direction the object's rotating. My thumb has to point toward me, away from the camera. So I would say the rotational velocity, omega, points toward me. You would say the rotational velocity points toward me. We all agree. If I reverse the direction, I have to roll my fingers the other way. My thumb points toward the camera. When the object rotates this way, my fingers roll this way. My thumb points along the axis of rotation toward the camera. You would say omega points toward the camera. We all agree. Let me rotate it a little bit. As this spins in this direction, omega points toward the camera. And if I rotate it, I would run my fingers around the wheel like this, and omega would point up along the axis of rotation. If I rotate it the other way, I would have to run my fingers in the other direction, and omega would point down. So the direction is always along the axis of rotation for omega and alpha, and it's given by the right-hand rule. And the same rules apply to omega and alpha that apply to V and A. When omega and alpha point in the same direction, doesn't matter whether it's positive or negative, when they point in the same direction, the speed is increasing. And when they point in opposite directions, the speed is decreasing.